Hello, everyone, and welcome to this new discussion where we are going to talk about a different subject today, a contemporary subject that is from last week, and that comes from an interview of Terrence Howard, whom I understand is an actor, artist in general, um, patent owner, and perhaps scientist, or at least clearly interested in the natural sciences. And perhaps self-proclaimed genius. I don't know. Um, so, of course, many people have talked about it, and what I would like to offer today in this discussion is perhaps a different angle with which to look at some of the discussions that have been happening online. Now, what I want to discuss today is essentially twofold. The first one is I want to look at a passage which is quite telling, let's say, about the way he talks about the natural world, and basically trying to use a notion that is called the notion of incommensurability of theories that has and basically try to analyze, let's say, the situation with regards to or with respect to this particular concept. And then once we've done that, then I would like to look a bit more at the things that Terrence Howard says about the chemistry, and in particular the way of presenting the chemical elements. And I want to use that as an opportunity to look a bit more into the work of Mendeleev, because I think this is like nobody usually has actually read what Mendeleev wrote. Usually, we've been told by our school teachers, whatever, what we should think of this Mendeleev table, why it works, why it doesn't, blah blah blah. And at the end of the day, we are quite remote from what, maybe at least from what Mendeleev actually wrote initially. So that's what I would like to discuss today. So first, let's have a look at just a portion of what Terence Howard actually says. So let's have a go.
We can. We couldn't do that before because we didn't know the angles of incidence that were necessary to open these things up. And you couldn't do that with the Platonic solids because the Platonic solids were averages and approximations. They, like I've said a number of times, you show me a real straight line in nature. If everything in the universe, everything is expressed in motion, all motion expressed in waves, all waves were curved. Every action has an equal and opposite reaction. So the greater the action, the greater the reaction. The greater the reaction, the greater the resistance. The greater the resistance, the greater the curvature. Because the universe is based off of equanimity, which Einstein left out in his theory of relativity, the balancing side of the gravity was caused by electric force. Electricity is always seeking a higher pressure condition. It spins northeast, is trying to get to the center of an area, the center of a cone. But the next electric wave is coming, so it gets pushed out, and as it's pushed out, it gets to the vortices. And that's some on those pieces, those vortices. Now, instead of it spinning northeasternly, centripetally, it's forced to spin centrifugally, and it spins southwesternly. And it expands itself out. It decays. It keeps decaying until you get four magnetic waves that hit each other at 120-degree angles. At that point, they reconvert back into the electric field. And then
Okay, let's stop here. So there are multiple things to be said here about what was just said. What I'm going to show here on the screen some of the reactions by physicists and scientist slash philosopher on X or or Twitter. Um, and the bottom line is that these people say that this is total nonsense, and I think for example Bernardo Kastrup has even called for this kind of discourse to be completely deplatformed, and so on and so forth. So there are a few things to consider. Um, as I think and people have mentioned that in the comments of many of these, let's say, more alarmed reactions. Um, the thing is that, when they listen to Eric Weinstein, or when they listen to even Brian Greene talking about string theory or whatever, it basically sounds exactly the same, like bullshit, if we will, as Terrence Howard is actually saying. Like, there is no difference in the level of confidence being displayed. There is no difference in the um, technical appearance of what is being told about, and complexity as well. And at the same time, there is also the same thirst, seemingly, for sort of beauty or symmetry. In fact, that Sabine Senfelder tends to dislike, but she probably has criteria of her own, which probably look like that as well in any case. Um, so if I listen to what was just said here, and I actually give the meaning to the words being pronounced. So, for example, gravity, electric field, curvature, and all of this stuff, and I give these words the same meaning than the ones I've learned in the theories I've learned of gravity, and the theories I've learned of electromagnetism, then this is going to be just incorrect. It's not, it doesn't matter whether it sounds gibberish or whatever. That's just incorrect. That's just invalid. That's not part of these theories. So that's something I can say confidently. Now, one possibility that I must consider, and that some people have kind of touched upon in some of the reactions, is that actually the meanings that he's ascribing, that he's giving to these different words, is completely different to the meaning I give to these words. And automatically, basically, it transforms what he says into literal nonsense to me. Um, and in fact, rather than calling that nonsense, because then there is a possibility that there is a sort of value judgment here, nonsense in the sense of this is total bullshit, I don't need to waste my time on this, etc. Here, this is nonsense in the sense that I can't make sense of it. And this is something that has been put forward by Paul Farabend as a concept known as incommensurability. And the idea here is that if you take essentially two languages, and you use these languages to describe the world around you, or to make statements about the world around you, then there are sentences in one language that basically are likely not to be translatable into the other language. And so you reach, in that case, a situation of incommensurability, whereby you call upon concepts in one language that have no commensurate, let's say, or equivalent, let's say, concepts in the other language. Um, and personally, that's how I would view what Terrence Howard is talking about here. Um, Essentially, there is incommensurability between the language he speaks, and the language I speak. And therefore, there is a near impossibility for me to evaluate actually whether what he's talking about is, you know, correct or not, at least on a priori or theoretical grounds, because the theoretical grounds I would have to use would be based on the concepts and meaning, etc., that are developed, for example, in the Maxwellian theory of electromagnetism. But here, he doesn't seem to be using Maxwell's theory of electromagnetism, because he says that magnetic waves can apparently somehow hit each other, whatever that means. Um, and then apparently when they do that, they convert back into an electric field, which again is not part of the theory, etc. So I prefer to view that this way. Maybe that's a polite way of saying nonsense, but I think that's the most careful thing that we can say. It could be that there are things to be learned in what is kind of claiming. Perhaps I would say that it's claimed a bit too assertively, maybe. Uh, But the point here is that we need also to look into the idea that here it doesn't seem to be, as far as I understand, in a sort of scientific endeavor. Okay, he's not in a situation where he's trying to communicate with others and kind of discuss the output of experiments and the possible interpretations, what that means in terms of what exists in the world and so on. He already believes that he has that already there. And most of the knowledge he's trying to impart on us here seems to be essentially revelation. Okay, so it's of revelatory nature from visions or dreams. So it's unclear whether this is something you would want to engage with anyway, this sort of kind of clashes that happen in science. Okay, so that's the first aspect I wanted to discuss. So basically incommensurability. And I think this is something very important that perhaps I will go into more depth in some other videos, because personally I think this is an overlooked notion. So let's look at some other parts where it talks about chemistry. So let's try to see here maybe.
Show the relationship that between every element, there's between every, there's two no.
All right, here's the periodic table.
You'll see hydrogen sitting all the way over there by itself, but they don't show that hydrogen has the same tone as carbon.
What do you mean by tone?
Same tone, same key of E. Same key of E. 40.5 hertz. The next one would be like 81 hertz. You go to silicon, it will double up and would be 162 hertz. You'll go to cobalt, and it'll be 324 hertz. It's, in that base, if you were to take the angles of incidence or the tones that they create, their color. Like you can turn color back into sound based upon, it's the same wavelength, it's just twice as long or much longer. So all you have to do is keep dividing light by 2.
Keep that up, Jamie.
You keep dividing light by 2, and you'll ultimately get back to the audible sound of it, because there was a relationship between light and color, sound and tone, matter and shape. I put, I sent over Walter Russell's.
I was trying to get to that. That's what.
Yeah, it's Walter Russell's periodic table that he put together. Now you compare that to what Mendeleev's periodic table. You'll compare Walter Russell's to it, and you'll see something completely different. It's unwinding.
Whoa.
It's unwinding. And you see there's a relationship that hydrogen.
So you had figured this out at a young age?
I had already seen this. This was all inside of that palace. I had access to it, and I knew the relationship.
So you saw this in dreams?
I saw it as a circle. Everything was a full circle laid out, and each area was just expanding, like wrapping a rag around your hand. The first wrap, it's so tight. The very first wrap is so tight. That's the first one that Walter Russell did, yeah. But go back to the wiggly one. This is how I saw it more so, but as a vortex. But you'll see there's a relationship between hydrogen, carbon, silicon, cobalt, rhodium. They're all bonded. They're all sit as the middle point between two noble gases. So those things don't really exist. It's only one substance. Now the problem is the first thing that we're able to perceive is hydrogen. That's the first visible element, because before it is too dense for us to perceive it. You understand what I'm saying?
Okay.
But as you reach into the next octave, the carbon octave, and they call that a bisexual tone, because the carbon has 2 tones to it. It has a negative side and a positive side, the part where lithium behaves.
Okay, so I'm going to stop here. But there are a few things to mention here. First of all, there seems to be a sort of depreciation of the work of Mendeleev here. And I think that this is really useful to actually read what Mendeleev actually wrote. And this actually leads me to um, talking about a few things. The first one is um, the current so-called periodic table. So the modern periodic table is going to look like that. Um, and in fact, if you read lecture notes, if you watch YouTube videos, if you've been to school, etc., at school, what you're going to be told is essentially this classification of the elements is based on basically valence electrons. And then there's a further subdivisions that can be made where you basically increase the number of valence electrons and kind of atomic number, uh, depending on whether you go down or horizontally and so on. And in doing so, you're actually, basically getting a structure out of it. You can get further structure by saying which blocks, let's say, which orbitals these valence shells, let's say, correspond to. So you're going to have the S, P, D, and F, for example, and that's what basically you're going to be told about. So it's essentially about electrons and kind of it's tied like very, very tightly to the quantum mechanical understanding of matter. And so it's almost a way of sorting out our quantum mechanical understanding of matter. Now, the reason why it's very different from, it turns out, is very different from the original table, periodic table from Mendeleev. Very different. And so here I show you what is the original table. It looks like that. And so you see, for example, that silver is exactly in the same column as hydrogen, which is absolutely not the case anymore. So it's quite different from the modern one. But what I would like to discuss is essentially what Mendeleev was talking about. Okay, so I'm going to simply read out some an excerpt from a lecture he gave, if I understood correctly, in 1989. And he actually summarizes what he did. So he published a book that in 2 volumes called Principles of Chemistry. Absolutely brilliant book. The first volume is essentially looking at all the chemistry having to do with the formation of salts, oxides, and also hydrogen compounds. And then the second book looks into the law of periodicity. And so let me tell you here what he actually says at the very beginning of the lecture. That was a Faraday lecture again in 1889. So without entering into details, I will give the conclusions I then arrived at in the very words I used. The elements, if arranged according to their atomic weights, exhibit an evident periodicity of properties. Elements which are similar as regards their chemical properties have atomic weights which are either of nearly the same value or which increase regularly. And we are going to see kind of what that means here. The arrangement of the elements or of groups of elements in the order of the atomic weights corresponds to their so-called valencies, as well as to some extent to their distinctive chemical properties, as is apparent among other series in that of blah blah blah, lithium, beryllium, barium, carbon, nitrogen, oxygen, and iron. And then there are plenty of other things basically. We must expect the discovery of many yet unknown elements, for example, elements analogous to aluminum and silicon, whose atomic weights would be between 65 and 75. The atomic weight of an element may sometimes be amended by knowledge of the contiguous elements. Thus, the atomic weight of tellurium must lie between 123 and 126 and cannot be 128. And basically that's it. So that's the summary of it. So essentially what he noticed is that if you were to place the elements and you basically put them in order of their atomic weights, which is something that he recognizes has been only available since the 1860s. Then basically he says that we should get a periodic, um, like periodic properties, a periodicity in the properties, which he calls the law of periodicity of the elements. So here I've actually played a bit and I've actually displayed what this should look like. And that should look like this. So here I've plotted only like few of the elements that were known at the time. And what I've actually deduced is the following. So on the x-axis, I'm actually plotting the atomic weight, and both at bottom and top, these are atomic weights. It's just that it avoids them from overlapping. And then at the top here, what I'm actually looking at on the y-axis, I'm looking at the number of chloride that or chlorine atoms you would get in basically in a chloride version of the elements you're looking at. So that would be, for example, if you take silver, that would be AgCl, so for silver chloride. Um, and you, for example, for cadmium, that would be CdCl2. So just to say that basically you can get the number N here in that particular chloride compound is going to be described here. As it turns out, this number N on the y-axis is also the number that arises in higher oxides, and so that you can form with these particular elements. And so that would correspond to a form of this where you've got the element here. So for example, silver again, and then you would have Ag2O2, whereby here the number 2 in the oxygen is kind of the degree of oxidation. No, sorry, Ag2O, sorry, and where O1 is basically the degree of oxidation. And you would have the same, you would have cadmium oxide, that would be actually cadmium dioxide, that would be Cd2O2, and so on and so forth. So that's something as well which is mentioned in this particular lecture, where he gives the example of this cadmium and silver, just to illustrate kind of how that works. Um, so what you see when you plot that, so that again, that would be the valency of the oxygen or the valency of the chlorine you would have in a compound with these elements, and essentially that what you observe is that this valency essentially oscillates. So it has a periodic kind of behavior, and it does look like uh, this unwinded version that Terrence Howard is talking about in this kind of revolutionary classification of the elements. Um, and it's just that, of course, you can write this on a strip like this, but it's not particularly useful. So that's why Mendeleev actually cut it essentially midway. So just before, for example, this particular series here is cut just before silver, and then essentially is put below rubidium and so on. And basically each time is going to be cut, and then each time like the period repeats itself. So each time you go here, you go up, and then you go up again, and then you go up again. So each time you've got a trend like that, up, you put it back below rubidium, and basically there is an alignment of the different elements here to play the same chemical role in experiments. Okay, so that's kind of the underlying idea that was put forward by Mendeleev. Now, there are a few things that are fascinating here. Mendeleev actually talks at the time as well of what about atomic spectra, and he says that there has been some attempts to link a classification that would be based on atomic spectra in the same way actually that proposed here by Terrence Howard. But what he says is that, well, the problem is that we observe that atomic spectra depend on conditions of pressure and temperature. And so in the 19th century, of course, you could not necessarily isolate the spectra, and it's not like you would get a single line either. And so what they said is that it's basically too murky to ground periodicity or the law of periodicity because it's not well defined enough and not well measurable enough. And so that's why he actually looked into that. Now, one final thing I want to say, this is quite a big paragraph. I will obviously put it to be read if you want to read it on your own out loud. And that's the following part. So, feeling that spectrum analysis will not yield a support to the Pythagorean conception, so here of a primary matter, that's the idea, its modern promoters are so bent upon its being confirmed by the periodic law that the illustrious Berthelot, in his work Les origines de l'alchimie, 1885, page 313, has simply mixed up the fundamental idea of the law of periodicity with the ideas of Prout, the alchemist, and Democritus about primary matter. But the periodic law, based as it is on the solid and wholesome ground of experimental research, has been evolved independently of any conception as to the nature of the true elements, of the elements. It does not in the least originate in the idea of a unique matter, and it has no historical connection with that relic of the torments of classical thought, and therefore it affords no more indication of the unity of matter or of the compound character of our elements than the law of Avogadro, or the law of specific heat, or even the conclusions of spectrum analysis. And what is fascinating here is that Mendeleev really insists that the law of periodicity that he's kind of explaining here and laying out in a table, and of course, if you just see the table, you don't see the periodicity if you have not plotted kind of the kind of things I've plotted, or if you haven't read the about 800 or so pages of his 2 volumes of Principle of Chemistry, then basically you're in trouble to understand these things. And what he insists on is that all of that is purely observational. There is, of course, some layers of vocabulary and terminology just even to talk about the elements, and that's something that Feyerabend, with this notion of incommensurability, which clearly would have noted. But what I'm saying here is that for the most part, it's mostly trying to tie in together experimental observations in the same way that Kepler, for example, with the laws of Kepler of orbital motion, captured mostly observational phenomena and linked together empirically, let's say observational periods, for example, of orbits, and so on and so forth, with the distance, estimated distance of the time between whatever the sun and moons and so on. Okay, so that's the idea here. In my view, the work of Mendeleev was absolutely brilliant. In the modern presentation, actually that we use today, we depart from the fundamentally experimental aspect of the law of periodicity. It could be that it's because it's not working, um, but I think that there is a problem with this departure. It's too grounded in theory in the modern presentation, and it's as if, for example, we were grounding a bit too much. For example, if we have the law of ideal gases in thermodynamics, it's an empirical law. And for example, if we observe that it doesn't work for some gases, that doesn't change the situation and the conditions within which this law is going to work. And so it's a bit problematic to ground a bit too much these things into theories, at least as far as I'm concerned. And I personally think that people should be taught more about the way of thinking of people in the 19th century And here again, like the beauty of this law of periodicity, as it is observed as a sort of curve, and then you can simply put a portion of that curve below the other, and then flatten the whole thing and transform it into a table. So on that note, if you've got any comments or questions, please do let me know in the comment section, and I will put as many information as I can in the description of the video as well. So otherwise, see you in the next video.